Happy Friday. Just to let you know, the Chapter 4 Learn Smart, I've actually extended that through Monday, so you have until Monday. If you finished it, good. We haven't quite finished Chapter 4 yet, so I want to make sure that we at least cover through today's lecture before you. I wouldn't want it to be due before you can really get everything. So, actually, I should ask you, how do you like Learn Smart? Yes, it's good.
Yep.
Is the amount I'm assigning too much or too little? Or just right? Because I'm sort of setting it intermediate in terms of level or depth of the material. If you think I should be having it allow you to learn more, I could certainly have it do more.
There's an option to add more.
Oh, you can add more?
Yeah.
Oh, that's
You
good.
can keep doing what you want.
But most importantly, I want to know, is it useful? And there's pretty good agreement that it's helpful. Good.
I just wish they would allow like synonyms.
Synonyms? Oh, I know.
That's You have to use the exact word. I mean, you could use like.
That's the one thing I didn't like when I was previewing it, is that if you don't use the word that the book uses. Yes. So unfortunately, there's not a lot you can do about that. Well, they could improve it. Actually, that's a good feedback. I'll give it to them. I would like to see that too. Because you might have a right answer, but it tells you you're wrong because you didn't use the same word that the book used. Yes. Okay. All right. I think that's all the announcements I have. Let's continue talking about alkyl halides. So you remember we were talking this week about the reaction of alcohols and how we can convert them to alkyl halides. And we discussed a lot of the details about this particular reaction mechanism. That is the SN1 reaction. So in this case, it's a three-step process where the first step really is just a pre-equilibrium. It's an acid-base reaction. The activation energy for that step is not that high, and so this is happening quite rapidly. The real reaction is taking place from here forward. That is, in this process, after we protonate the alcohol, the CO bond breaks. So it goes through a transition state where that bond gets longer, and then we form an intermediate carbocation. Okay, and then that carbocation is still reactive. It's seeking electron density, and so the chloride that's left over in this particular example reacts with that in the second step to form the products. Okay, this reaction the rate of the reaction is dependent only on that step that involves the CO bond breaking, and so when we think about how that affects the rate of the reaction or the kinetics of the reaction, it's only involving one species, so this is what we refer to as a unimolecular reaction. Since the rate only depends on this one molecule, then it's referred to as an SN1 reaction, or unimolecular. Substitution, nucleophilic, unimolecular. Okay? And the rate of the reaction is largely affected by the stability of that intermediate. Okay? We talked a lot about what the factors are involved in increasing the stability of a carbocation that's generated. So that's the intermediate along the way. The more substitution you have on there, the more stable it is, the lower in energy it is. And that's due to essentially delocalizing the plus charge by inductive electron donating from the carbon through the sigma bond. And if you recall, the hydrogens that are on those, the electrons in those bonds can sort of overlap a little bit and neutralize that plus charge to some extent, or at least lower its energy through hyperconjugation. Okay, so the energy of that intermediate that's formed is directly affecting the transition state to get to it, because it's an uphill reaction path from that step, from the protonated alcohol to the carbocation. So the energy required to get to the intermediate is also reflected in the transition state energies for those. Okay. So this reaction to form this intermediate largely depends on how stable that intermediate is. And if that energy gets too high, there may be other pathways present. So we were talking on Wednesday a little bit about how this reaction mechanism we just talked about to form the carbocation intermediate actually could be diverted to a different path where we don't form that intermediate as a separate step. And that's the difference, particularly when we look at methyl and primary alcohols. Because that carbocation is much higher in energy than the others, that the reaction mechanism changes slightly. So the first step, which is very fast, okay, the protonation of the alcohol, still is occurring just as before. But the important step, the rate determining step, is the second step. Instead of breaking the CO bond to form the carbocation, okay, that's not happening because that's too high in energy. It takes a lower energy pathway where this is all happening in one process. That is, the electrons from the bromine are starting to form a bond with the carbon. At the same time, the oxygen bond is breaking. And so we've combined those two steps into one. And so as a result, the reaction rate is depending on more than just one species. Okay, you can see the rate expression here, some rate constant for this reaction, times the concentration of the protonated alcohol times the concentration of the bromine. So both are important for the rate. And so if you look at this this is to the power 1, this is to the power 1. Overall, it's a bimolecular reaction. So the rate expression is second order overall. That's why we refer to this as an SN2. Substitutionally, feel it's bimolecular. Okay? And here's that energy diagram to show that step. So the pre-equilibrium here to protonate is still happening. But that process then from the alcohol that's been protonated to the product is just one step, not two. The transition state reflects the bond forming from the carbon to the bromine and the bond breaking of the CO bond. And overall, that's going to be a little bit lower than actually forming a carbocation. If you were to compare this example, if R is a carbon, for example, on that substrate, it would form a primary carbocation. If it were to go through the intermediate process, it might look like something like this, where that's the carbocation, and then down to the product. So this is a little bit lower in energy, and that's why it takes this path, as opposed to forming a discrete intermediate. It does this all in one step. SM2 process.
That's generally just for the methyls, 1G prime.
Methyls and primaries, because those would be the least stable carbocations, and so that would form a lower energy pathway by just doing it all at once. Yes?
So I remember a question where they were saying which one was going to use the SN2, and they had a butyl.
A butyl, but was the OH on the primary carbon or a secondary carbon? Yeah, if it's on the primary, if it's the general rule of thumb to remember, if it's a primary or methyl, it's going to go by an SN2. It can't, the carbocation is too high energy to go by SN1. A secondary could go by either mechanism, which sometimes is some gray area. We'll talk about that much later in the class. And the tertiary will definitely be a carbocation formed. Okay? There are other ways to make alkyl halides, and they involve a similar kind of process. So the way we did it with hydrogen halide is we have an alcohol. That alcohol, the CO bond is made weaker or easier to break by protonating it, because then you could cleave or release a neutral water, right? Well, this is another way to do it, but instead of a proton going onto the alcohol to activate it, we have these reagents that can do that, as well as provide the halide source. So thionyl chloride, SOCl2, does this reaction to convert an alcohol to a chloride. And phosphorus tribromide can convert an alcohol to a bromide. Those are convenient reactants because we can, they're relatively stable reactants that we can purchase and use from a chemical company. You can do the alternative also. For example, you could have SOBr2. That's fine, but it's a little bit more reactive and harder to deal with than PBr3. But you could certainly do this as the exact same concept. As well, you could probably do this with PCl3. So that might be interchangeable there. But how is this reaction working? Okay. We need to somehow react with the alcohol to make the CO bond easier to break. And then we have to provide a source for that halide that's going to react. And I'll just tell you right now, these reactions work best on methyl and primaries because it involves an SN2 substitution reaction. And something else, in the case of using thionyl chloride, we usually add something else in here. So you notice that the byproduct in this reaction is hydrogen chloride, HCl. Actually, we add something else to this reaction to neutralize that HCl. It's a base that we call pyridine. It's an organic base. The structure of pyridine looks like this. It's a relatively weak base because all it is this nitrogen lone pair is able to accept the proton. It reacts with HCl to form a pyridinium salt. This is now less reactive or neutralized form of HCl. Okay. So you'll often see this written with pyridine over that reaction arrow, for example, or pyridine added to this reaction. That's the role of the pyridine. So I'll just let you. I'm not going to worry too much about the pyridine part because I'm more interested in what's happening with the alcohol and the SOCl2. So let me erase all this and show you how this reaction works. The mechanism. So if we take something like methanol, I'll just take the simplest one. Come here. Okay. What happens is methanol reacts with thionyl chloride, the structure of which looks like this. Now, by virtue of the fact that there's this SO double bond, and oxygen is more electronegative than sulfur because it's higher up on the periodic table, that is highly polarized in that direction. Okay? As well, the chlorines are electron withdrawing also. Okay, so what do you think? Where is the area on that molecule that has positive charge? The sulfur, right? All these groups are pulling electron density away from the sulfur. So, let me erase those because it's clouding the issue. So, if you want to form a bond with an oxygen lone pair to the electrophilic site, it's going to react on the sulfur and push those electrons up onto the oxygen. Okay? But we also have on that sulfur a relatively weak bond that can leave. So those electrons, while initially pushed up onto the oxygen, actually will come back down and cleave the chloride. So oftentimes we won't even see, might not even write these arrows here. This will attack the sulfur and the chloride will come off. Okay, the intermediate that's formed is this. Now, this intermediate initially has a plus charge on the oxygen, formal plus, and the byproduct now, the thing that came off was chloride, right? Okay, then now there are several ways to write this. So you could envision that now undergoing this SN2 substitution, where the chlorine will attack the carbon, kicking off that oxygen. Okay? That's one way to write this. Your book actually writes it slightly differently, but I'll show you this first. That will form, we're going to run out of room here. That'll form the chloride plus this, And now this, notice the other byproduct is SO2. This decomposes. If you think about that pyridine base, okay, you'll get the hydrogen proton transferred to the pyridine, and then the electrons that were in the OH bond form another double bond to sulfur, and then chloride comes out. That forms SO2, and then the pyridine salt of HCl. Okay. Your book actually draws this slightly differently. Your book takes off the proton first. So, hope I'm not scribbling too much here. The pyridine base first reacts to neutralize that O+. And that's perfectly legitimate as well. As a matter of fact, if you have the pyridine base present, that may happen quite fast. Regardless, what we still have now is an alcohol where the proton has been replaced with an SOCl group. That group is still electron withdrawing and would want to take those electron density away. So that's still weakening the CO bond here. Okay? If that bond is still being weakened, then the chloride, and if you follow all my electron movements, the chloride can react on the carbon. That kicks off the CO bond towards the sulfur, and then that chloride comes off. So that would form exactly the same thing. Okay, so have you followed all this? The essential reactivity is very much the same as our reaction with hydrogen halide. We somehow activate the OH so that we can break the CO bond by reacting it with some electrophile, something seeking electrons. In this case, it's the plus charge, the positive character of the sulfur, or in hydrogen chloride, it would be the proton. And then chloride has the ability to react at the carbon, kicking off the CO bond. Okay? These byproducts, forming a gas, SO2, actually helps this reaction proceed because that bubbles out of the solution. But the essential aspect of the reaction is the same. This is an SN2 substitution reaction where the Cl carbon bond is forming at the same time the CO bond is breaking. Okay? And that's what I want you to connect those general reaction concepts, even though we've changed some of the reagents slightly, the reaction mechanism concepts and where electrons are flowing really are much the same. Okay, the PBr3 example. This is the same. Phosphorus tribromide is an electrophilic reagent. Okay, these groups are more electronegative than the phosphorus, the bromates. So if you have an alcohol with a lone pair, right, you're going to react that electron density of the alcohol with the electron deficiency of PBr3. That's going to be at the phosphorus. And again, we can do this. If you react that at the phosphorus, we can break a phosphorus-bromine bond. Okay, what does that form? That will form our alcohol. Again, something like this. And then what's happened is it's another way now to make the CO bond weaker. It's just the same. Now we have a third way to think about making that CO bond weaker. We've made a bond to an electrophilic phosphorus. Bromide then can attack the carbon at the same time break the CO bond. So it's still an SN2 reaction, just like the case if it has a proton on there, or if it has this SOCl on there, or you have a PBr2 on there. Okay, the same process is happening. So that will form the product, in this case, methyl bromide, the product. Eventually what happens is all three of these bromides react and three of the OH groups get put on there. And so we end up after doing that 3 times with that phosphorus reagent, we end up with phosphoric acid as the byproduct. H3PO, sorry, not phosphoric, phosphorus, right? H3PO3. But what's important to recognize, again, is what's happening with the carbon-based group here, the organic molecule. The alcohol being converted into a halide by activation of somehow to make the CO bond weaker, and then a nucleophile replacing it. In this case, bromide. In the top case, chloride. Okay? Any questions about that? I will probably be more interested for you to remember the details of the HCl and HBr mechanism. If you remember these reactions, I think what's important to recognize is that SOCl2 replaces OH for Cl or OH for Br on a primary or methyl substrate, okay? Because it's SN2. Okay, so those are nucleophilic substitution methods for doing a conversion of a functional group alcohol to a hydrogen to a carbon halogen bond. There are other ways to make organic halogen compounds. One of them is doing direct halogenation of alkanes. And I mentioned this reaction a little bit before. I want to talk about more details of this process. This is of what we call a free radical halogenation. Free radicals are reactive species which have unpaired electrons. And so what's happening is instead of doing reactions where we're moving 2 electrons at a time to form bonds and break bonds, we're actually breaking bonds homolytically to give 1 electron to each atom of the bond that's breaking, and then forming bonds between radicals and things like that. And so what happens in this process is you can do chlorination directly of alkanes. It takes a lot of energy because it is a high energy process. You can heat this up to about 400 degrees. Okay. Or the reaction can be activated by light energy. So we could add a photon of light, or photons of light. Both of those ways to activate the reaction are doing something with the chlorine here. Chlorine gas, Cl2. In order for this reaction to take place, Cl2 has to break apart. So when Cl2 breaks apart into 2 chlorine radicals, okay, we use a dot to represent an unpaired electron. 2 chlorine radicals, just to give you a little more detail, this breaks apart. If you think about the bond between them, right, there are 2 electrons in that covalent bond. One goes to this chlorine and one goes to this chlorine. Notice my electron flow arrow only has a half of an arrowhead. That's indicating 1 electron movement. Okay, remember that? That takes a lot of energy. You can heat it up to 400 degrees, or certain light at certain wavelengths will do that as well. Once you generate that, then these reactive free radicals can react and interact with organic halogen compounds. And you'll notice one of the things about this process is it's not that selective in terms of what kinds of products it can form. HCl is one byproduct because we've replaced a hydrogen with a chlorine, and then that hydrogen has to go somewhere, so it's the other end of the chlorine. The main reaction product is, in this case, chloromethane. But if you really look carefully, you'll see traces of other things present when you do this reaction. You'll see dichloromethane and trichloromethane and even some tetrachloromethane. Okay, so all those things do get produced, although this is the major one. Okay. Free radical species, by the way, are electron deficient because if you break the bond, if you break the chlorine bond this way, let me draw the other electrons around chlorine, you have 7 electrons around it. It's not an octet. So when you have free radicals, you don't have a filled octet. So you can imagine that they're going to be reactive species, right? Okay, let's talk a little bit more detail about the free radicals. Similar to carbocations, which are electron deficient, the same trend of stability of a free radical on a carbon holds true. That is, the least stable free radical is the one with just methane, a methyl radical. Okay? As you put more and more carbon groups on there, the stability of your free radical gets more. That is, the energy goes down. Becomes more stable. For the same reason that a carbocation becomes more stable. Okay? You have a carbon which is deficient of electrons. It's deficient of only one electron instead of two, like a carbocation, but it still doesn't have an octet. So the same way that we stabilize a carbocation by adding more alkyl groups around it, we stabilize free radicals. So this is the similar picture of a free radical as a carbocation. The radical here, you can imagine there's one electron in this orbital. It's planar. It's a p orbital, generally. P orbital. So if you have this also a p orbital with one electron in it, not empty, but with one electron, you can have the same effects, inductive effects, and more importantly, hyperconjugation from the adjacent groups. So again, additive, just like it is with a carbocation. So this is a good thing. It's the same concept that stabilizes both carbocations and carbon radicals. Okay? So you can imagine then different hydrogens on different carbons might react differently. Let's see, I don't remember the order I have my slides here. Okay, let's take a look at the enthalpies of the bonds. That is, different kinds of bonds. This is a table from your book. Different kinds of bonds have different bond energies based on the substitution around it and the types of atoms. So if you look at this chart, here's just some diatomic molecules to give you some comparisons. So when we're talking about Cl2, the chlorine bond has a bond dissociation energy, right? The energy required to homolytically cleave it, of 243 kilojoules per mole, or 58 kilocalories. Okay. Actually, that's weaker than an HCl bond. HCl bonds under polar conditions, where you're talking about protonation and 2 electron processes, easier to do. But if you were to break apart an HCl bond to form free radicals, it's actually harder. And that's what this is reflecting. Notice these alkanes here. If we look at the energies of the CH bonds, and the one that's highlighted here, so a methyl CH bond, 105 kilocalories per mole. A primary CH bond, which is reflected by those two, about 100 kilocalories per mole, or 101. So it's lower in energy, a little bit weaker. Okay? Let's see, a secondary carbon-hydrogen bond, weaker still, and a tertiary carbon-hydrogen bond, even weaker. Why do you think the CH bond would become weaker if it goes from a primary hydrogen to a secondary hydrogen to a tertiary hydrogen? For the same reason, when we talked about the alcohol SN1 reaction, the activation energy to get to the carbocation intermediate is lower if that carbocation is lower in energy. Same thing here. This energy reflects forming radicals. So if you form a more substituted radical, it takes less energy to get there. That's reflected in the bond strength of the CH bond. Okay, it's all related. This is the rest of the chart. There's the alkanes again. A carbon-halogen bond, about 84 kilocalories for a Cl bond. A Br bond is 70. An iodine bond is 57. Those are relatively weak in terms of reactivity. Notice the fluorine bond is very strong. Fluorines are a whole different As a matter of fact, when we talk about reactions of these halogens, and fluorines are kind of in a different category because their bonds are quite strong. But the important point I want to mention here and reiterate is that the strength of the CH bond depends on what kind of hydrogen it is, primary, secondary, or tertiary. So let's take a look at some of these bonds, this reaction with something besides methane. If you do this free radical halogenation with chlorine gas and butane, you actually have two products. There are two constitutional isomers for the monochlorinated product. So if you replace one hydrogen with a chlorine, you can get that chlorine on one of the N carbons, so it's a primary chloride, or you get that chlorine on one of the middle carbons, the secondary chloride. So it's one chlorobutane or two chlorobutane that's the product. Right? So if you just think about statistically the chances of forming those, on butane we have a CH3 here and a CH3 here, and two hydrogens here and two hydrogens here. So there are 4 equivalent secondary hydrogens, and there are 6 equivalent primary hydrogens, right? And if it's just a matter of the statistical probability of pulling off one of those hydrogens and replacing it with a chlorine, you would expect to have a ratio of those two products of 6:4 or 3:2. Okay? That would be your expected ratio just based on that statistical number of hydrogens. In fact, when you actually carry out the reaction, you find that ratio is nowhere close to 6:4. It actually favors the secondary chloride by more than a 2:1 times. So 30:70 is the actual ratio of those two products that are formed. Why? Because in this reaction process, you break a CH bond. A secondary CH bond is weaker than a primary CH bond, and so what that means is that, and if you calculate out the statistical difference from what you expect and what you actually get, secondary hydrogens are 3.5 times more reactive than primary hydrogens for chlorination. Okay, we see the exact same thing. Here we're comparing 9 primary hydrogens versus 1 tertiary hydrogen. Okay? So you would expect this ratio to be 9:1 of the two possible products. And in fact, you get something nowhere close to that. 9:1, we actually get about 2:1 ratio, or 65:35. Okay? You look at that and you say, well, okay, that means the one primary hydrogen must have been more reactive than the 3, or the 9, the one tertiary hydrogen has to be more reactive than the 9 primary hydrogens, and if you calculate that out, it's about 5 times more reactive for a tertiary hydrogen to be pulled off than a primary. Okay? And that makes sense thinking about our bond enthalpies and the CH bond strengths. Oops, let me go back, I missed that. Okay, so this process, as I said, is a free radical process which involves several steps. One of them is initiation of the reaction by breaking the Cl-Cl bond. Okay, by heat, 400 degrees Celsius or higher, or light energy. That's what we refer to as an initiation reaction. When we talk about free radical chain mechanisms, that's what we refer to as an initiation reaction, because we start from no free radicals and we're generating 2 free radicals by breaking a bond. Okay? So again, homolytic cleavage, 1 electron from that bond goes to each of the chlorines. Okay, then what happens? Once you generate a reactive chlorine radical, how do we get the substitution on the alkyl halide, or the alkane? Well, the process occurs by propagation steps. That is, we react a reactive radical Now, this chloride radical with a stable molecule with no radicals, and you can imagine that chlorine pulling off a hydrogen with one electron. That forms the HCl bond. Okay, and if it pulls off a hydrogen with one electron, sorry, my arrows look terrible there. Then we have formed or left behind a carbon with one electron. So we've taken a radical species and a stable molecule, generated a new stable molecule and a new free radical. Okay? So in that case, we start with a reactive intermediate. We've generated a new reactive intermediate. It's a chain propagation type of process. Okay. How do you get the chlorine on? So we've broken the CH bond. Now we have to get the chlorine on. And so what can happen is that the new reactive Cl, or the carbon radical, can react with chlorine to form a new bond, one electron each. And that breaks to form another radical, chlorine radical. So here's our organic product. We've generated still a free radical. That's why it's called a chain reaction, because that can go back again to the previous step, methane, in this case. Right? This goes back into the reaction, and we take that off to repeat the process. And so that happens over and over and over again. So theoretically, if you break one chlorine molecule, Cl2, to chlorine radicals, that reaction should go forever. Right? As long as there's alkanes to consume. But it doesn't, and it doesn't because once you start generating free radicals, there are chain termination steps which occur when you have two radical species combining to form a stable molecule. Okay, that doesn't generate in the process something that's still reactive. So, for example, if you just combine the carbon radical plus a chlorine radical, you get chloromethane, and nothing can go further. So that's why it's referred to as a termination step or termination process. You could do this in a lot of ways. If two chlorine radicals combine, right, you just reverse the process of the initiation step. That also is a sort of a dead-end pathway. So that's why reactions don't go forever. So we often need to keep heating reactions or keep applying light to get the reaction to go to completion. Okay, I want to pick this up again next week. I want to have a quiz now, so we will take a quiz, and then you can have a good weekend, right? So lucky you for sticking around for the long weekend. Take some of the hand back. Oh.